Let's learn about calibration curves. Now, I know this may catch you a bit off guard. I mean, we've been talking about solution preparation, instrumentations. How the heck did calibration curves come into the mix? Well, I've noticed a lot of confusion about what calibration curves do, what types of curves are there, and why are they important? So, here's the game plan. I'm going to introduce you guys to the principles of calibration. Then we're going to discuss a few types of calibration curves: linear, linear through zero, logarithmic, exponential, and polynomial. Then I want to spend a moment talking about how do you know if you have a good calibration or not. Now, here's the reality. Calibration curves are usually vital for quantitative analysis. If you're trying to figure out how much of something you have, odds are you need a calibration curve. It's really used to determine the concentration of an unknown. And how is that done? To create a calibration curve, you need something called standards. Standards are solutions that you make or purchase that have a known concentration of target element. Generally speaking, one would use a low, medium, and high standard, although there are cases where you'd use more. What happens? Well, let's look at this graph over here. On the y-axis, I have emission counts. Now, let's just call this counts. These are the numbers being spit out by a certain instrument, the raw numbers. On the x-axis, I have concentrations of standards in parts per million or milligram per liter. I have prepared three concentrations. A blank, which I guess is not a concentration at all actually, a 0.5 milligram per liter standard, and a 1.0 mg per liter standard. Again, these are solutions that I have prepared. What happens then? Well, the blank gives me a certain amount of counts. The 0.5 milligram per liter standard gives me a higher amount of counts. Why? Well, we have more analyte in there, right? The 1.0 milligram per liter standard gives even more counts. Why? Well, we have even more analyte in there. As a result, the analytes are giving off more signal. Plot this information together and you have a calibration curve. How do I use this? Think of this as a prediction curve. Once you've built a calibration curve, now you analyze your sample. You don't know how much sample you have. You don't know what the analyte concentration is, but we can use the calibration curve to extrapolate the unknown concentration. Pretend that my sample is giving counts of about 2.5 times 10 to the 5. Well, I don't know right off the bat what 2.5 means in concentration, but hey, look at that. I built a calibration curve. I can simply extrapolate out and see at what point does my sample emission intersect with my line. Drop down as follows, and you'll see that you can correlate this to the x-axis, the sample concentration, which in this case is about 0.246 milligrams per liter. Now, here's the issue. Do you notice that the calibration curve in the last screen was kind of linear, kind of straight? Well, that's not always the case. Curves can be curvy. They can be U-shaped. They can be sigmoidal. They can be all over the place. How do you know which type of a curve to fit to your points? How do you know that your points are linear or not? Well, this depends on the type of analysis you're conducting, the detection limits, and the hardware specifications. Let me give you a bit more information. Certain analysis types, such as metals analysis, rely heavily upon linear calibration curves, like the one you saw. That's just how the analysis is, the range you're working in, how the elements behave. But if you suddenly move to a biological analysis, well, biological analysis doesn't tend to be very linear. It tends to be more sigmoidal. For instance, if you're measuring cell growth, well, cells will grow, and after some time they'll plateau, they'll run out of resources. So that would not be a linear curve anymore. You may also have hardware specifications. I have a metals background, so I'm going to talk a bit about metals over here. Certain instruments, such as AAs, rely heavily upon exponential curves, upon twisty curves. Other instruments, by their very design, like OES and MS instruments, are designed to be linear base up. They don't work well if you try doing anything that's nonlinear. But generally speaking, You will find linear curves and nonlinear curves. That's about the two major types you'll find. Let's talk about something called linear calculated intercept. Now, a linear calculated intercept is your basic regression curve. It follows the formula y equals mx plus c, where y is a dependent variable, in this case counts on my y-axis, x is my independent variable, or my concentration on the x-axis, m is the slope of the line, and c is the y-intercept. Can you see it? You may want to pause the video and just take a look. The y-intercept here is not forced. What do I mean? I am not jamming it through a certain point. In a linear calculated intercept, the y-intercept is calculated by the other points. The curve ends up on the y-axis wherever it wants to. This kind of a curve is often used in clean and low concentration applications, usually in GC, LC, UV-Vis, depends upon what you're doing. I wanted to mention a quick note. Please keep in mind that depending upon a geographic location, the y-intercept may be designated as B or as C. It really depends upon which part of the world you're in. That is to say, if you see an equation such as y equals mx plus c, that is the exact same as writing it as y equals mx plus b. It again is simply a function of which part of the world you're in. Then you have the almighty linear through zero, which is represented by the equation y equals m of x. Again, y is your dependent variable or your counts, x is your concentration, and m is the slope of the line, delta y over delta x. Linear through zero, as the name suggests, either forces or pivots around zero. You're really jamming a curve and pushing it through the 0 point. Why? Why would one use this curve? Yes, inherently they are not as accurate as simple linear curves. You are forcing a curve. But sometimes you don't have a choice. In certain applications, your background or your bogus counts may be so high that your y-intercept may be completely unusable, at low levels anyway. In this case, you pick the best of both worlds. You pick the better of two evils and say, hey, instead of going for inaccurate low concentrations, I'm going to go for less inaccurate low concentrations. You force it through zero. You'll find this heavily in spectroscopy-based techniques, specifically ICP-MS, ICP-OES. Not as much in other techniques. Then you have the nonlinear curves, logarithmic, for instance, which follows the general formula y equals m ln x plus c, or log x plus c. Long curves, I've shown you just an example down here, but honestly, they can look pretty radical sometimes. By this point, you know what y and x are, you know what m is, and you know what c is. I'd like you to stop and just look at the curve. Do you see the 3 points? Imagine I tried forcing a straight line through those points. How would I force it? How could I conceivably get a straight line that would magically hit the low, medium, and high standards? I wouldn't. You have to use a nonlinear curve. In this case, the way the points are is best represented for a logarithmic curve. Exponential curve is the little brother to logarithmic curves, which follows the general formula of y equals c e to the power mx. Again, take a look at the points. We have a low, medium, high point, don't we? Try forcing a straight line through. Can you visualize it? Can you visualize a straight line hitting all the points, coming even close to all the points? No, right? They would either be dominated by the high point or you'd be forcing a bit towards the lower points, but it's not going to work very well because in reality the points are kind of curving, aren't they? Well, in this case, an exponential curve is a better choice. Then let's move on to the polynomial equations, which come in many flavors. I'm just showing you a quadratic variant as represented by the equation below. Takes you back to high school, doesn't it? It's been a while. Again, look at the points. Do you think you could force a straight line through them? I mean, doesn't look very straight to me. Doesn't look very linear to me. I guess I could force it, but it would be quite inaccurate, wouldn't it? No, the shape of the curve is more polynomial in nature. And again, this is a quadratic variant. These curves are found more in immunoassays, biological systems, cell cultures, and can have multiple orders. Now that I think about it, logarithmic and sigmoidal curves, which I've not discussed, can also be found in more biological systems. With that out of the way, let's talk a bit about assessing calibration curves. Now, you may have heard of terms such as coefficient, correlation, correlation coefficient, R squared, R this, R that. These terms are quite misused. Let's talk about what they mean. Now, calibration quality is assessed by something called coefficient of determination. This is R squared. It's assessing variability of the goodness of fit. Essentially, it's asking, hey, does my chosen curve really follow the points? Think back to the logarithmic or exponential curve. What do you think? If I force a straight line through those points, would it really follow any of the points, or would it end up somewhere strangely in the middle? R squared ranges from 0 to 1. Closer you are to 1, better your curve, better your points and your traceability to the curve type. Calibration quality can also be assessed by something called coefficient of correlation, or simply correlation coefficient, also known as R. I should point out I've seen this confused quite often. I've seen R squared referred to as coefficient correlation, etc., vice versa. No, R squared is simply saying, are my curves following the points? Whereas R, or coefficient of correlation, is asking, are my two variables, x and y, moving together? In simple terms, R is an indicator of the strength of the relationship between the two variables x and y, whereas R squared is an indicator of strength, goodness of fit, of the curve. R squared ranges from 0 to 1. R can range from -1 to 1, because you could hypothetically get a negative curve as well. Let's look at some practical examples. I'm working with R squared over here, keep that in mind, goodness of fit. Over here, R squared, the closer it is to 1, the better your curve is. My R squared is 0.9959, which is actually quite good. Rounds off to about 0.996. This means that, for the most part, my points are tracking the curve really well. Over here, this is an okay fit. I'm not too thrilled with it. R squared is 0.9643. That's really not the greatest. As you can see, the curve isn't matching the points well. The points are beginning to go further and further away from the curve. Now you have a real rubbish fit. R squared is 0.9067. That may sound like, oh, 0.9 is close to 1, but look at the curve again, how far the points are from the curve. This is more likely a logarithmic or exponential type curve, would be my guess. But clearly a linear curve fit through 0 is not working well. I would pick a different type. Now, folks, it is good operational practice to verify a calibration curve after you perform calibration. I'm talking immediately after calibration. Why? Well, your calibration could have been a fluke. Perhaps we have instrument drift that's taking place. Perhaps the sample intro component that's failing that gave a false calibration. In any case, performing a quick check to ensure that you can trust a calibration curve will save you hours of analysis times. How do you do this? Well, really, it comes down to analyzing a known standard. You could ideally prepare a fresh standard from a third-party source, one that's been validated by an outside agency. You could also potentially rerun an existing standard, although quite often people just run both. The second one is definitely less preferred than the first. See how your standard responds. Now, this response, depending upon your industry, is considered recovery. Really, you want your recovery or your response or your error to be less than 5% of your target calibration value. So for instance, if your calibration value is, let's say, 50 parts per billion, the max error I really want to see is plus or minus 5% of 50 ppb, which is 2.5 ppb. Now, keep in mind this error margin can be extremely instrument dependent. It can be extremely industry or regulation dependent. So do your due diligence first. Some industries will tolerate errors as high as 10%, sometimes even higher. Others are very, very strict about an error margin being less than or equal to 5%. Personally, for me, I really want my error to be negligible, at best. A calibration is usually performed using ideal solutions, a best case scenario for analysis. If your calibration itself is compromised or you can't trust it, well, how would you trust any data generated using that calibration curve? So validation is extremely important. Throw some final points in. R squared and R are important, but they are not the only means of evaluating calibration curves. They are arguably two of the more popular ways of doing it. Curves can be influenced very heavily by high points as well. That's something I really want to emphasize. A high concentration point will have high intensity, high counts, high whatever you have on your y variable. This means you could erroneously influence a curve by a high concentration point. Be careful. Keep in mind that most calibration curves need to be validated or checked with a quality control standard right after calibration. And keep in mind that ultimately, goodness of fit may be what it is. You need to validate your curve. You really need to test it and see, does it hold?